Okay, so we are back to the 2012 multiple choice no calculator question number 17. So in this problem, the figure shows the graph of f, and f is defined to be a definite integral. So by the FTC part 2, f prime is equal to g, and we are given the original function f, and we're supposed to figure out which could be the derivative, which is g. Since we have a linear function, then we have a constant slope, and since the linear function is increasing, the slope is positive, so we are looking for the graph of a positive horizontal line, and that is A. In number 18, classic definition of derivative. It is the point-specific definition of derivative. And here, if you look down here, you can see, no pun intended, the format of the point-specific, one format of the point-specific definition of derivative. So the C value in this case is 4, so it's point-specific. Derivative of what? So we remember that's the question we ask. F of x. Actually, this should be f of c in this particular case, not f of x. So f of c is sitting back here. So the function is what we get when we take the 4 plus h out and put x back in. So we have the function is ln x, and the derivative of ln x is 1 over x, and then we substitute 4. Number 19, we have f original, and we want to know what points on the graph have the property that the line tangent has a slope of 1/2. So this is really just a fancy way of saying when is f prime, excuse me, equal to 1, I'll never be able to do this, equal to 1/2. Oh, I did. So we find the first derivative using the quotient rule, down d up minus up d down over down down. You can see that in my work below. We have to clean it up. We're going to set the first derivative equal to 1/2, cross multiply, take the square root of both sides. Don't forget to, whoops, sorry, didn't mean to jump. So right here, take the square root of both sides. Don't forget plus or minus, and set x plus 2 equal to 2 and x plus 2 equal to -2. You get 0 and -4. Those are your x values, and they have to be substituted into the original to get the y values. So that's the key for getting those correct. Number 20, we have f of x is an original function, and g is the inverse of that function. The x's and y's switch places. We have an initial condition, or a condition, of 0, 1, and we want to find g prime of 1. So if you're in my class, if you're smart, you make a chart. So the x value of 1 belongs to g according to the prompt, meaning that that's a y value on f. We know the x value of f is 0, that's given, so the y value of g has to be 0. So we find the derivative of f original by the chain rule. You can see that. Derivative of the outside times the derivative of the inside. We find the derivative at the x value of 0. And partner points on inverse functions have reciprocal slopes. So since the slope at 0 of f is 6, the slope of g is the reciprocal of 6, which is 1/6. 21. Y equal 5 is a horizontal asymptote of which graph? So we're looking for a horizontal asymptote, which is all about end behavior. If these are rational functions, we can talk about top heavy, bottom heavy, same heavy. So a is not a traditional rational because we have sine 5x in the numerator, so I'm going to leave that one alone. I know that y equal 5x is linear, so it doesn't have an asymptote. I can see that c is rational, and it is bottom heavy. Therefore, the horizontal asymptote is 0, so it can't be 5. In number 5, I see that we have a same heavy function because the power of x in the numerator and the power of x in the denominator is the same. So we take the quotient of the leading coefficients, which is 5, over -1, which makes -5, so that one's out. And then lastly, we have same heavy because the degree in the numerator is the same as the degree in the denominator. So we take the ratio of the leading coefficients Be careful, the leading coefficient in the denominator is 4, not 1, and 20 over 4 is 5, so we have our answer, and we don't ever have to worry about A. 22. Let f original be a quotient. What is the absolute maximum? So here we are looking at the EBT. We need critical numbers and endpoints. So in this case, I find the first derivative using the quotient rule, as you can see down here. Down d up minus up d down over down down. Simplify. Set the first derivative equal to 0. And we also have to consider the denominator. Remember, a critical number is anything that makes the first derivative 0 or undefined. So I set the numerator equal to 0. Subtract 1, divide by -1 right here. And e to the first, when we undo the logarithm, e to the first is e, so we have an x value of e. And what makes the denominator 0 is 0. However, 0 is actually not in the domain of this function because you can't take the ln of 0. So when we make that number line to examine this, I'm going to start at 0 because you also can't take the ln of a negative number, so the domain is numbers that are greater than 0. So I put e on the on my number line as a critical number. I pick a number in each region to test out and determine that I'm going from positive to negative, so I can see that the absolute maximum has to be or has to occur at e. Or, oh, wait, yes. The other mistake is it doesn't ask for the x value, it asks for the actual value of f. So once you figure out that the absolute maximum occurs at x equal to e, you have to substitute it back into the original function to get the y value, because that's what they're asking for here. 23. P of t is the size of a population at time t. Which of the following differential equations? So they're giving us a derivative, and we're looking for linear growth. Now, a couple of ways to think about this. You did not have to do what I did here. But in order to have linear growth, remember the slope of a line is constant. So that means the derivative, if we're having linear growth, that the slope of that line has to be constant, and the only constant that we have is 200. In 24, g is a function. Pay close attention. G is a product. K is a constant. For what value of k and g does G have a critical point at x equal to 2/3? Well, a critical number, we need the first derivative, so I did the product rule right here. We're going to set the first derivative equal to 0 to get critical numbers right here. You're going to need to factor out that common factor of x e to the kx. Set each factor equal to 0, so the first factor equal to 0, second factor equal to 0. And then they told us x is 2/3. So I'm going to take the 2/3 and I'm going to substitute it in place of x. And I'm going to substitute it in place of x. And I'm going to solve for k. Now remember that e to a power cannot equal to 0. So that's why I got rid of that. And then I'm solving for k on this side over here. And when k is -3, this condition is true. 25, which of the following is the solution to the differential equation 2 sine x? So I'm going to separate. It says integrate, but I think it's supposed to be integrate, solve, and solve. And you can see the work here. We have initial condition of pi 1, so we're going to substitute to find the value of c. 26, g is a function given with the first derivative. Which of the following must be true on the integral? So g prime is given as a definite integral. So in this case, when we do FTC part 2, it takes us to g double prime. The derivative of g prime is g double prime, or the second derivative. And so for g original to be increasing, that means g prime has to be positive. And for g to be concave up, the second derivative also has to be positive. So if you look down here at my second derivative, e raised to the negative at any value of x that you, any value of x or any number, I'm sorry, that you substitute in place of x will generate a positive value. So, because e to a negative x squared can't be negative. It can just, that negative power just takes you to a fraction, but doesn't make it negative. And then for g prime, again, since e to the negative t squared is a positive function, then the area would always be above the x-axis, so g original would be positive. 27, we're given a differential equation right here, and they want us to find the second derivative. So to find the second derivative, we're going to get dy dx by itself by dividing both sides by x plus 2y. Take the derivative by the quotient rule. Notice that I have a dy dx here and a dy dx here. So when I substitute the numbers, I actually don't substitute. I don't take this big expression of dy dx and substitute it in place here, because that would be really messy. I actually substitute the 3,0 in place of dy dx here. And then when I'm doing my other number substitution, like here and here, the dy dx, I just bring from what I calculated back over here. So you just need to take a minute, sit there and look and study that to see what I'm talking about. It's a little bit easier than trying to put that big expression, excuse me, back in place of the second derivative. 28. We have a position function given, and we want the acceleration. We have some, at the point where the first, or the velocity is equal to 0. So we find the first derivative using our trig derivatives, and we're going to set that equal to 0. Now, you don't have a calculator, so you have to figure out when are sine and cosine opposites of each other in order to make 0. And if you think about your unit circle, they're opposites of each other in the second quadrant and in the fourth quadrant, but it says up here first equal 0. So the first time we get 0 would be in the second quadrant, which would give us 3 pi over 4. And then I'm going to find the acceleration by finding the derivative again of the velocity function and substituting 3 pi over 4. So you have to know your trig values and be careful there. All right. And that takes us to the end of 2012 Part 2. Hope this has been helpful for you.